We'll start in a minute. Okay, it's 3 p.m. So we can start week 12 on the technique of material characterization. So before I start anything, there was last time a question was asked by the Uday, and there was in my explanation there was some problem is there. So now I would like to clarify that thing, and let's go to the question first. Uh, Ahmed, if you have any doubt, please ask, and if there is a noise is coming from your side, if you don't have, then please mute a little bit. So yeah, so what we can do is let's see what was the question first. So the last time I made a mistake and while the explanation part. So the question was that this is atomic scattering factor, and on the x-axis we are writing sine theta by lambda, and the curve is going something like this. The question was that why f is decreasing when sine theta by lambda is increasing. How I explain? My explanation was from the penetration point of view, like low angle, less penetration, high angle, more penetration. But in this week, we have learned the concept of absorption, that absorption factor, which says that the diffracted beam will be free from these factors of like the penetration, because in the first case, in the case one, where the angle is low, the X-ray is spending more amount of time, even though the angle is less. So here the penetration is less, but the time spent by the X-ray is more. Here, in this case, the time spent is less, okay, but the penetration is more. So this both the factors will cancel out each other, and there won't be any absorption part. Okay, so now, so this explanation which I gave, it's not true. Let's go to the explanation part. The explanation part is that it's an atomic scattering factor. So we have to see it from the perspective of the atom. So whenever an X-ray beam is passing and there is an atom is there, nucleus, and then there is an electron. We saw in the week 10 that the kind of beam, that the kind of intensity profile they are going to make. If it is straight, if it is a forward scattering, there won't be any the intensity will be like quite intense. The X-ray intensity which you are going to get is will be quite high. There will be the constructive interference. Now as we are moving away from as we are our scattering angles keep on increasing, we can see the intensity of the diffracted beam is also keep on decreasing. It has to do with the how the X-ray is going to interact with the electrons. So see, we say that n lambda is equals to the 2d sine theta, right? What is this n lambda we are just putting so that Bragg's law should be satisfied, right? N lambda equal to 2d sine theta. What is 2d sine theta? If we don't equate with the n lambda, what does it mean? It means that the path difference. So the thing here is that as we are increasing the theta, so part difference is proportional to, we can say that the theta, sine theta. So in other way, we can say that the path difference is proportional to the theta. More is the theta, more we are moving away from the forward scattering, our path difference will keep on increasing. And more is a path difference, there is a chance that from that perspective, that it will try to go under the destructive interference. Okay. Okay. So this, so the it has to do with the path difference. Path difference is keep on increasing as we are increasing the theta. And this is the reason why, as we are moving away from the, as we are moving away from the forward scattering, theta equal to 0 to the higher angle side. So we are getting that, okay, the intensity, the atomic scattering factor, which is the scattering from the atom, is keep on decreasing. Okay. So this is the true explanation. The explanation which I have saw this explanation multiple times, like in my BTech time and also in couple of the videos, uh, like few NPTEL videos. So now, but I'm convinced with the explanation by the in this particular course, and so that's why we are rejecting this particular part, because they both of them, the absorption part, the penetration part, and the time spent by the X-ray, they are going to cancel out each other. Those two effects will nullify each other. And we saw that when we are talking about the powder diffraction in this particular week, when we are talking about the powder diffraction, there is no dependence of the absorbance on the theta. Okay, we only saw the absorption dependence in the case of the cylindrical part. Okay, cylindrical sample when we are using. Okay, again we are going to discuss this thing, cylindrical thing and the flat part. So this is the major explanation which was given by the professor in the week 10. So the uploaded doubt solving sessions of the week 11 which I did, and week 10 also, which where I explained things in this way, I will modify that. And so we should be aware about the fact that what is the true explanation for this. Okay. So now we can move with the week 12 contents. These are the list of the content that we have covered in this particular week. Last time I told you that the temperature factor we not taken into account in the week 11 dot solving session, but this time we are going to do that. Okay, how the temperature factor, how the temperature is going to affect the intensity. Okay, intensity of the X-ray, the affected beam we are talking about. And then there is the absorption factor, which we will discuss. After that, these are the mostly the things that we have done, like for example the atomic scattering factor, the structure factor, the multiplicity factor, and the temperature factor we are going to study, and the absorption factor. This majorly we studied for the ideal crystal, where we involve the mathematics, like majorly it is mathematic part. But now, after a while, we'll try to understand about the diffraction from the real crystal. Real crystal is the one which is having some, the first thing is that it have finite size. And second thing is that it has a defect associated with it. These defects can be grain boundary, it can be surface, it can also be the dislocation, and it can also be the point defects. Okay, so these things we are this thing will come under the defect part. Okay, so this is how our real crystal is going to be vary from the ideal crystal. And again at the end we studied little bit about the EBSD. We just saw the glimpse of the EBSD, what it can do. Okay, so before I start with the my explaining the concepts and doubt solving things, I would like to ask you that do you have any doubt in the content that has been covered till now? Let me turn on the comment part. Okay, very good. Now since there is no doubt, let's move ahead. Let's discuss about the temperature factor first, then we'll try to solve few questions based on that. Yeah, so we can see here this factor e to the power of minus of 2m is plotted on the y-axis, and on the x-axis we have plotted sine theta by lambda. Okay. Now we are seeing that as we are keep increasing, as the theta, as we are keep increasing, the theta is more and more, this the factor is going more in the fraction part, like decimal part. So this is the term which we have to multiply. This is the term which is taking care about the temperature part. So whatever the intensity, let us say I intensity which we will get, I naught, let's say we are getting, we have to multiply that I naught intensity with this factor of e to the power of minus of 2m if we are taking the temperature factor into the account. Now you can see that as we are moving to the higher angle side, this factor is becoming the fraction more, it's decreasing more and more. It means that it is going to decrease your final intensity. If this is decreasing, so your final intensity will also decrease. So higher angles are going to get affected more. So let's see this part. So e to the power of minus 2m, this is a factor by which the calculated extra intensity must be multiplied to account for the reduction in the intensity due to the thermal vibration. So what is happening over here? The distance between the atoms, let's say initially u naught, if we increase the temperature, they will vibrate, their mean position will again change. It will, let's say it will go to some u position. We usually see the diagram, we call it as a potential well. When they are when the two atoms are very far apart, let's say this is the distance between the atoms. Okay, when they are very far apart, they will close to the zero. When they will try to come each other, they will form the this type of well. Okay, so this type of this is a potential energy, we can see. So now we can see that the maximum potential is occurring at some particular r naught. Okay, now let's say I increase the temperature. So initially two atoms are sitting at the distance of r naught. If I increase the temperature, what will happen? It means that I'm increasing the temperature, it means that I'm giving it a additional energy. So the energy which used to be here, since I gave the additional energy by the thermal, now it will go somewhere here. So now the atom has a two position to vibrate along, right? And their mean position will somewhere over here. If I increase this further, see their mean position will again shift. The in between them it will be somewhere over here. If I again increase the temperature, mean position will, okay. So our mean position is keep on increasing. We can see our mean position is keep on increasing. So about which it can vibrate, and that is again like we know that lattice parameter, the distance between atoms, it is something which consider the will going to affect the unit cell, and so it's going to affect the d spacing. Since our this factor is changing, the distance between atom is changing, so entire our XRD patterns, they are going to affected by it. Okay. So now, so we have to multiply this intensity I naught here I consider to be the static intensity, where the let's say that theoretically the intensity which we will get at the absolute temperature 0 Kelvin, okay, multiplied by e to the power of minus of 2. Then we will get the final intensity which is affected by the temperature. Okay. Now this factor is known as the Debye-Wohler exponent. Now it is a function of the atomic position of an atom in sine theta by lambda, and this is going to change. This is going to change with the temperature. So with respect to the temperature, how it is going to affect it, and how in response to that how m will be affected, in response to that m our intensity is going to be affected. Okay, so this is how entire thing are related with each other. Again, one can relate that, see, this is sine theta by lambda. One can relate with the Black's law that okay, we can write that lambda equal to 2d sine theta if we are considering the first order of reflection. Then sine theta by lambda we can write as 1 over 2d is equal to the sine theta divided by lambda. I just rearrange the term. Lambda I brought over here, 2d I brought over here. So this one can replace with the 2d. So let's try to revisit this graph. As we are moving ahead, It means that as this term is increasing mean that the D is decreasing. As D is decreasing, we are seeing that this factor is also decreasing. It means that the hour intensity will be decreased to the larger extent. So this region is the one where the the temperature factor effect will be more. Here the temperature factor effect will be less. Now one can ask me that why as D is decreasing it is going to affect, right? If less is the D, more is the effect. So for that, see the D spacing is low, D is low, and lambda equal to 2D sine theta we know. This vibrations which we are giving with the thermally at higher temperature, now it can significantly affect this U over D. This can significantly affect this entire term. The small vibration can affect the smaller D value more effectively compared to the larger D value. And this is the why that if I keep on decreasing this D, the entire term overall is going to increase, and so it can lead to the destructive interference. Okay, so the position is going to be the smaller D value, the smaller D, the plane which are separated with the very small D spacing, they are going to be affected more. Okay, even with slight change in the U compared to the one which is at the higher D, the interplanar spacing where the D values are quite high. So these are the two important points which I wrote. Thermal vibration cause greater decrease in the reflection intensity at the higher to theta angle with respect to the lower. So here the intensity will be lower, and here here the intensity effect will be more, and so the overall intensity, since we are going to multiply with the fraction value which is low, the intensity will be low. While here the intensity will be on this side, the intensity will be the higher. Okay. Now one more thing. Low temperature, I mean the low melting point material have the higher U value. What does it mean? This is something which we need to keep in our mind so that we can solve the couple of questions. The statement is low melting point material have high U value. U is the atomic displacement. Let's try to draw a graph. First one I will dive. Let's draw the tungsten. Tungsten is the one which is having the high melting point. The graph will go something like this. Now, if I draw, let's say for the lead we know it has the low melting point. The graph will go something like this. Okay. So here we can see that this is the again U. This is the energy part. Okay, don't confuse this U with this U. So now if I increase, so this is the one which is having the lower melting point. Here the high melting point. So lower multiplying have the higher U. Small increase in temperature will result in more amount of displacement. A small increase in temperature will lead to the more amount of displacement. Small increase in temperature, the displacement will not be to that larger extent. Okay. So this is what it means. It is how this potential well is created between the high melting point and the low melting point. So among these two, low melting point and the high melting point, which one is more temperature dependent, like very temperature sensitive? whose diffraction pattern, XRD pattern, will be more temperature sensitive, whether the low melting point one or the higher melting point one. Can anyone answer for that? Our XRD pattern is going to be affected because of mu over T, right? So the lower the temperature, if the temperature is low, if something is low melting point one, in that case we saw that there is a huge displacement will be there. So this one is the one which is going to affect the XRD pattern to a larger extent, while the high melting point one will not going to affect that much. Yeah, that's right. So Gitu has answered that it is a low melting point. So this is what it means. There's a low melting point, have the higher U value. So it means that it will be more effect. Like if I draw for the lead, here the reduction in the case of lead, the reduction in the intensity will be significant. Will be significant compared to the reduction in the intensity which we talk about the tungsten. Okay, this is what it means. Okay, very good. If any doubt in this particular entire thing that we have discussed, guys, please let me know.
Here, my voice is audible.
Yeah, please go ahead.
The temperature we are giving to the specimen, right? It is based on the above room temperature. It means, or we can say even the room temperature is high. Then here we have any intention to increase or decrease the temperature to get any advantage in that structure elucidation, or just we are knowing that one uh, based on the temperature, what is the consequences are happening.
Very good. Yeah, this is a more like a practical type of questions which people usually have doubt on. So even the room temperature is high for certain material. For the for your that first question, for example, lead room temperature is also itself high. So in the class we have saw one example. I don't remember which was that at the room temperature it is 6% the displacement between the which was supposed to be R naught, and it went to the R is higher. R naught is at the temperature of 0 Kelvin, and this is at the 273 Kelvin, which is room temperature. So here if the increase in the displacement is more or less like the 6%, that is also going to affect our D spacings and all. Now, why to perform temperature dependent measurement? This was one of the question. For example, let's say let's consider one of the example, like you have the two material with you, barium oxide, let's say, and you have TiO2. At room temperature, they will, if I mix the two powder, they will be if in the container, the powder will be BaO and TiO2 mixture. Now, if I want them to react and to form BaTiO3, and I want to know the kinetics, like at what temperature this is happening, when this transformation is beginning. So in that way, what you can do, you can take the XRD pattern. Let's say this is at the room temperature. Now you can take the XRD pattern. Let's say at the 300, or you can increase the temperature based on your step size. Okay, and you might find that maybe later on at high temperatures, you will find the peaks of the BaTiO3. And it might be possible that some of the things are still over there. Some of the peaks are still over there. And if, let's say this is at the 600. Okay. I'm not thorough with the numbers, like and at what temperature it's going to transform. It's but all we should remember right now is that that it's after a while it is going to transform. Maybe at the even higher temperature now, the entire peak of the red one, which was supposed to be of the BaO and TiO2, they will disappear, and what we will get is something like this. Okay, so you can you can know the kinetics. You can find the kinetics part at what temperature things are happening. Also, you can hold at particular temperature, and you can, with respect to the time, you can take the XRD pattern. So and then at that thing you will know that at what time, what is the rate, at what rate it is the transformation is beginning. There are the multiple things you can do. Also, you can take your sample. You can like there is a stage will be there. Mostly it is made up of the platinum, in which you are going to keep your sample, and the platinum will be heated. The platinum plate or that strip will be heated by passing the huge amount of current through it. And due to that particular temperature rise, our sample temperature will also rise. So they will have a particular type of setup. Usually, most of the XRD people they have the setup to increase the temperature of the sample, and with that we can measure the kinetics, and you can do a lot of studies like this is one of them. There is also a study like if you have something reduced samples, okay, let's say SNO2 it was supposed to be, but it is SnO2 minus X, and you want to know at what temperature this is going to convert to the SN, at what temperature. So it can give some rough estimation that okay, it will give some change in the peak intensity, the peak position, so on and so forth. Again, the study itself will be very complicated. Okay. But this is one of the example which is quite simple, and we can know the at what temperature the reaction is going to occur. Is it clear, Ahmed? Any doubt? Please let me know.
That's clear. Thanks a lot.
Yeah, great. Let's solve one question based on the concept that we have learned. What is the primary effect of the thermal vibration of atom on the X-ray diffraction peak? It causes significant shift in the peak position. It primarily reduces the intensity of the diffracted beam. Okay, it eliminates the background scattering completely. None of the. So what we have saw over here that the intensity is keep on decreasing, right? Like the temperature thing is that if we keep on increasing the temperature, if I keep on increasing the temperature, what is going to happen that the intensity of the diffracted beam is going to reduce. Okay. Okay, this is a primary. Also, one can say that A can also occur under certain conditions, certain constraint. But on the larger scale, we'll say that if we keep on increasing the temperature, our intensity will keep on decreasing. Okay, so the right answer will be here, the option B. Okay, so this is how our thermal vibration is going to affect. Yes, Hemant.
Here, one more point. If we are keep increasing the temperature, if the specimen melt will happen, or we need to know when it is melting, we need to increase the temperature. Before reaching to the melting point, we need to play on it.
Yeah, very good. This is also one of the practical questions. So before you do XRD, so wherever you are going to do the XRD of high temperature, they will ask you the data of the DSC and TGA, so that they know that at what temperature the things are going to happen, like whether there's some transformation or maybe the melting point. Based on that, let's say it's something like that, like you have the barium carbonate with you and you are heating it, you will convert it to the barium oxide and CO2. The XRD operator won't allow you to do this type of measurement because the emission of the CO2 is not good for the entire setup. So he will ask you the data DSC. He will say, okay, these things are happening. He will directly reject, okay, we cannot do this because of the safety purpose. Okay. So you should be aware about the parameters. You should be aware more about your specimen as much as you can. Okay. So without the DSC data or TGA data, the the high temperature XRD, people won't even allow you to. Okay. Same. Same for everyone. Okay. Great. Okay. So let's have a look on one more question. The temperature diffuse scattering is more problematic for which of the cases temperature diffuse scattering is more problematic? Low angle, high angle, 60 degrees some particular angle, or all of the above? It is problematic at all of the angle. So what do you think? Which is the more problematic, most problematic? We can see over here. So we can see at what angle the effect is quite significant. Depending upon that, we can answer the question like the temperature diffuse scattering will be more problematic in what cases, whether it's a low angle, high angle, or some specific angle. Yeah, please answer guys this question. The temperature diffuse scattering is most problematic very good. The right answer is option B. So Gitu has answered this. Okay, nice. So we can see at the higher angle, the effect of the temperature is more significant with respect to the lower angle. Here we have to multiply with the larger fraction. So the R intensity is going to be decreased by a larger amount. Here the fraction is more or less close to the 1. Okay, more or less close to the 1. So at the higher angle one are the more problematic. Okay, very good. Let's go to the next part. Question number 2. For which material would you expect the decrease in the diffracted intensity due to the thermal vibration to be less prominent at a given temperature? So the temperature is fixed. Which will have the less effect? Tungsten, lead, both of them will have equal effect. Neither would be affected. For which material would you expect the decrease in the intensity? Decrease in the intensity will be more. Sorry, decrease in the intensity should be the less. So we have to focus on this word, less. What do you think, guys? For which of them it is going to affect very less? Okay. So you guys have wrote the answer to be the B, but it's incorrect, right? We have saw that. Yeah, very good, Ahmed. The right answer is option A. I don't know where I wrote. Yeah, this one. See this one. We know what we saw that the XRD pattern won't get affected in the case of the high melting point with respect to the one which is at the lower melting point. It is due to the potential well that has been created, the structure, the way it's there. Okay, so here the right answer will be the A, the less prominent. If I would have wrote the question to be the more prominent, which is the more prominent, in that case the answer would be the B. For the less prominent, answer is A. Okay, very good, guys. Let's go to the next part. So now here we have to talk about the Debye-Scherrer method, cylindrical specimen we are talking about. Okay, how does the absorption factor behave with respect to the diffraction angle 2 theta? So here we can see, let's have a look. Let's say this is our specimen. This is the screen. This is an X-ray. In the case of first case, forward scattering, low. Okay, the 2 theta is here is less. Okay, so here now this is the case 1. Now case 2, case 3, case 4. What we can see here, the amount of the sample here, the X-ray need to be passed this much amount of thickness in the specimen in the case 1. In the case 2, it has to pass comparatively less. Case 3, it will be even less. Case 4 is even less. Okay, so as we keep on increasing the diffraction angle, our intensity is keep on increasing, right? So this is what we are talking about, the cylindrical specimen. Let me tell you one thing. Uh, right now, in the present, most of the XRD, 99% of the XRD, they are use powder method, powder diffraction. It's very less people which use this type of things. Okay. So yeah, again, so here we can say that how the absorption in the case 4, 3, 2, 1. Absorption is like this, or absorption is like this. A or B, which one is the correct one? In which case more absorption is there? A or B? Please, sorry, I not show the screen properly. So in the case A, there is a more absorption. Like in this pattern, there is a more absorption, or this. Which one is the right one? Here, the sample, the thickness is quite large. Like it has the accident to pass more, so it has to travel more thickness. Here, the thickness is less. Either the thickness is even less. Okay. So in the case 1, the absorbance is very high. Okay. So what we can say that the intensity in the case 1 will be low. In the case 2, the intensity will be even. Okay. So what we can say that the 4, 3, 2, 1, in this case, like as we keep on increasing the theta, our absorption is keep on decreasing. Less absorption is for this particular angle. More is for this. Okay. So as the 2 theta is increasing, or theta is increasing, absorption is decreasing. Okay, and so we can say that the intensity will increase. So now we can answer this question. That how the absorption factor is going to affect with respect to the theta. So we know it decreases as the diffraction angle keep on increasing. So as we keep on increasing the 2 theta, in the case of cylindrical specimen we are talking about, if we keep on increasing the 2 theta, then this particular absorption factor will keep on decreasing. So right answer here will be the option B. Clear guys? Any doubt, let me know. Okay, good. We can move ahead. Let's go to the next part, question number 4. Before that, let me show you something. There are the two XRD pattern here, the first one and the second one. The first one is for the real crystal and the second one is for the ideal crystal. Here we can see only at the particular Bragg angle the constructive interference is going to happen, and at the remaining all the angles it will be destructively interfere and the intensity will be 0. While here we can see that at Bragg angle there is intensity is there, sharp intensity is there, but even at the non-Bragg angles still there are the few intensities are there. Okay, there is a like a peak type of thing is there, a broadening type of thing is there. In the ideal crystal we can see there is a no broadening, but in the real crystal we can see that the broadening is there. Okay, so this is the difference between the ideal and the real crystal. Now let's try to answer the question. I will put it at the same position from where I took it. What is the most significant visual difference between an ideal X-ray diffraction pattern and one from the real one? Okay, significant difference we need to point out. Please go ahead. Tell me which one is with the right answer. A, the real specimen pattern has the peak at completely different to theta. The peak position is changing, they are saying that. Now, the ideal pattern has the highest peak intensity. C, The peak in the real specimen pattern has a finite width and dark border. The real specimen pattern lacks the background scattering seen in the ideal pattern. What do you think? Which one is the right answer among this? Which one is the, what we can say, that the significant, most significant difference? Yes, yes, very good. Chandrani, Ahmed, and Geetu, yeah, everyone answered it. The option C is the right answer over here. Okay, nice. See, this is also a, if the most significant if part I remove, then option B is also the right answer. Okay, but the most significant is the one which is here we are going to see. The intensity again, it will decrease. Uh, the highest, the line intensity I'm talking about, not the area one. Okay, the line intensity is going to decrease. Okay, this was the question number 4. Let's go to the question number 5. What is the full width at half maximum of an XRD peak defined and measured? How is the full width at half maximum is defined and how it is measured? The linear distance across the peak at its base where the intensity is 0. That's again the same thing. So the first one is telling that the linear difference between the base intensity, like it's telling that this is the full width at the half maximum. The angular width in degree or radian of the peak at the half of the maximum intensity. Yeah, Chintrani and Gitu has already answered. The option B is the right answer. It is the, we'll take the what is the highest intensity. We'll go to the half of it, half of the if highest intensity is 100, let's say, then we'll go to the 50. Okay, and then at that point we'll see that what is the width. What is this particular width? This is it can be measured in the degree, also in the radian. Okay, so here the right answer is option B. Okay, you very good. Now, why this broadening is happening? Why this broadening is happening? One of the effect is the crystallite size. One of the effect is the crystallite size. Okay, so for example, let's say that we have the, let's talk about the ideal crystal. Ideal crystal will have the infinite amount of the planes. Okay, so let's say this is a Bragg angle, and the n lambda equal to 2d sin theta is satisfied, and the XRD peak we are getting the intensity. Slightly away from that, if now we are moving the angle just little bit ahead of it, if we are increasing the 2 theta, in that case what is going to happen, that the Bragg's law is not satisfied. It will find, say, let's say the part difference is right now between the first one is that, like, the, in the case of diffraction, what should happen, it should be the lambda. Okay, let's say the n lambda equal to 2d sin theta, and lambda, the part difference is lambda. But now let's say in the case of when we moved away from the Bragg's angle, when we move away from and we move to the theta, let's say something, let's say we move to the theta. In that case, what will the power difference will be? It will be the lambda, it will be there, plus some delta d will be there. Okay, now it will find some from below, it will find a plane which is whose difference will be the lambda plus lambda d plus 1 by 2 of lambda. So now it will find the peak, it will find a position, it will find the X-ray, like the power difference whose will be like this. Now they both are going to interact destructively. So the destructive interference will happen for any theta which is away from the Bragg angle. Now for the ideal crystal, sorry, now for the real crystal. The real crystal, the problem is that the number of plane is fixed. Okay. So initially when we were moving away from this particular Bragg angle, Initially, we were able to find the peak who is going to destructively interfere with this the one which is not at the Bragg angle. But while it went quite down and searched that okay where the destructive interference is going to happen. While in this case, when the number of plane itself is fixed, let's say only this much amount of plane are there. Initially, the destructive interference peak was coming from, well, like the wave X-ray was coming from this. So now it won't be able to come. So it's not going to cancel out. So even since the destructive interference is not going to happen, it means that the intensity will not be zero. It will have certain intensity, and that is the reason why it is going to form the hump. Now using this, there is a formula like the derivation we not did in the class, and also if someone is interested, then I will suggest that the BD quality there is a book on the X-ray diffraction. The derivation part is given in that, and it's beautifully explained the entire part. So from that we can find the crystallite size, like the size of the crystal, the crystallite size. The term is this crystallite size is quite it has a the definition is quite what we can say that it's not very complicated, but right now since it's not explained in the class, I should not speak or else will deviate in a different direction. So this crystallite size is, I will only tell that this is the one where the coherent scattering is happening. Coherent domain size. Coherent diffracting domain size. So it will here in this particular range, it will give the coherent scattering. Okay. Now that crystallite size you can find with respect to this one. Okay. So now, so B here is we can know that the B is a broadening, B is the theta B is the Bragg angle, and lambda is the wavelength which we have used. Okay. So based on this, we can find the crystallite size. Now let me tell you that if defect is more, if we are increasing the defect is more, the crystallite size will decrease. Okay. The reason which was diffracting coherently is going to decrease as we are increasing, as the more and more number of, let's say, dislocation has increased in the specimen, more and more defect has been increased in the specimen. In that case, more defect, the crystallite size will keep on decreasing. So this T term will keep on decreasing. Also, as we keep on increasing the defect part, if the defect is keep on increasing, the B FWHM will also increase. So note this. We should note it down that if defect is increasing, then our B, the full bit at half maximum, is going to increase, and the crystallite size T, which we are referring to the crystallite size over here, it is going to decrease. This is the size of the domain which is going to give the coherent scattering. Okay. So for example, this much, now it's only this much is the one which is going the coherent scattering. Okay. So this was the entire thing that we need to discuss right now. If any doubt in this entire thing, please let me know. Okay, since there is no doubt, let's move ahead. Let's try to solve the questions. True or false? In an ideal, defect-free infinite crystal, the X-ray diffraction peak would consist of the perfectly sharp line, the zero width, at the Bragg angle. Defect-free, ideal crystal, infinite crystal, okay. The diffraction pattern would consist of the perfectly sharp line. Very good. Right, ML. Answer is true. Yes, yeah, right, Gita. The answer is true over here. So we have seen in the ideal crystal, we are getting a very sharp line. Okay. And now again, this is ideal. So let me tell you one more thing, like just additional information. A single crystal, single crystal tend toward the ideal crystal. Single crystal mean that, like, the polycrystal mean it have multiple number of grain. Single crystal mean that there is a single grain. Okay, there is no grain boundary. Okay, when I'm saying the no grain boundary, I'm referring to the high angle grain boundaries. Okay, certain defects will be there in even in the single crystal. The defects will be there. Certain amount of defects will be there, which can affect. That's why I'm telling that it's tending toward. It will try to achieve the ideal crystal, but it won't be able to do so. Okay. So, and one more thing, if you take a single crystal of sufficient size, you can get the intensity, the peak intensity will be so much. Like I recently did for the TiO2 single crystal, where I got the peak intensity to be the 5 lakhs. While if I do polycrystal TiO2, I only get around 10,000, the maximum intensity, the number of count over here. Okay, so this is a large amount of variation is there in the case of single crystals and the polycrystal. Okay, the maximum intensity I'm talking about. Okay, okay, good. Let's go ahead. Let's go to the next part. Question number 7. If the crystallite size in the material decreases, okay, the crystallite size is decreasing. What happened to the full width at half maximum? What will happen to the abbreviation? What do you think? We have already discussed this. FWHM, yeah. So Gitu has responded. The right answer is option B. That's true. Crystallite size is decreasing. It means that the FWHM will keep on increasing. Okay. They are like we can relate. If you see that, okay, let's say you saw in your pattern that XRD pattern, the case one is like this. Well, the case two is like this. So we can see that in which case, the case 1 or case 2, which one is having the broadening, more broadening. So we got to know that case 2 is the one which is having the more broadening. It means that the case 2 is the one which is having the low crystallite size. Which means that our specimen 2, will have more defect with respect to the specimen 1. Right? So this is how we can relate the XRD. Like you can just see your XRD and you can conclude certain small stuff. Okay, crystallite size, how much it is, like whether it's more or less, peak has shifted to what angle. Okay, right side, so volume is the expansion or the contraction, lattice expansion is happening or the contraction is happening. Now again later on, if you want to quantify them, like what is the crystallite size, so we for that we have the Serre formula, Serre equation. We have this, we can do. If you want to do even in the more precise manner, you can go for the with refinement. So a lot of things are there. Okay. But at the first glance, we should be able to make certain, like based on the observation, we should be able to make few amount of discussion part. We should know, okay, like what it's going to interpret. So this was the question number 7. Let's go ahead. Let's move to the next part. Question number 8.
Here one more
Yeah, yeah.
doubt I have that 7. If it is a nanoparticle, very fine nanoparticle,
Yeah.
that means it will looks like a broadening, right? Nanoparticle.
If we keep on increasing the size of the particle, it means that the crystallite size we are decreasing, the size of the crystal we are decreasing. Each particle is a crystal, so it means that it will go the more hump type it will go. So
Okay,
whenever
that's
in the
good.
class also we saw the example of, I think, ZNO or ZNS something, where from the ideal crystal, it was deviating like the hump was created as we are moving toward the nanocrystal part. Yeah. So
But
here,
here the hump is
yeah, yeah, please go ahead.
here the hump, if it is coming, is it reaching to the our objective or still it is become complex?
Actually, I not got. Can you please repeat?
If the peak broadening is there, our objective is what to find to getting the crystallography information. So when the peak broadening is happening, so our objective is become complex or it is become easy. When it is become a low size, the crystal size are decreasing.
Uh, See, everything is giving you the information. We cannot say that our objective has. It might be possible someone for someone the first one is more interested. Someone case two is a more interested. It's not like something got difficult or anything. It's just that how you are going to do your fitting with certain software, how and how you are going to interpret your data. Okay. So for example, let's say someone's aim is that to do the ball milling, and then after each ball milling cycle they want to measure the XRD, and they want to see what is going to happen. So initially they will get the particle size is quite large, they will get the something, the hump will be like this, the XRD peak will be like this. Now they ball milled it, the particle sizes keep on decreasing now. So what they are saying that okay, they have got something like this. So with respect to the particle size and all, like as we keep on decreasing, this thing is what going to happen. So it's just that what a person want to study. Okay, great, nice. Okay, let's go to the next question. Question number 8. For a bulk single crystal with a physical size of 1 mm, the peak broadening due to the crystallite size effect with respect to the 500 Armstrong. So the bulk single crystal with a physical size of 1 mm. When we have 1 mm size, the peak broadening due to the crystal. Okay, where is the question? For a single crystal with a physical size of 1 mm, the peak broadening due to crystallite size. Okay, we want to comment on this thing. Which one is the broader? Whether the 1 mm one or the 500 Armstrong one. In which case we will get a more broadening in the peak. So you have the single crystal. One is having the 1 mm thickness, and another one is having the thickness of 500 mm, 500 Armstrong. So in which case the peak broadening, for example, the FWHM, in which case FWHM will be more. Can anyone comment on this? Yeah, very good, Ahmed. That's right. In the 500 case, it will be the crystallite size. Sorry, the broadening will be the more. Okay, very good. So with that, let's go ahead to the next part. Now, strain part we have to discuss. A specimen can be strained. Okay, we know that every specimen will have certain amount of stress which is contributing toward the strain. The strain can be of two level, macro and it can be micro. Macro mean that it is at the larger scale we are talking about for the entire specimen. Micro mean that we are talking for a particular region. Let's say that, okay, let's draw this microstructure. A microstrain can be associated with a particular region, and it can be associated with each grain. While for the macro, we are talking about the entire specimen, the strain of the entire specimen. So now, they how the XRD peak, like seeing the XRD peak, XRD pattern, how we can comment upon the macro strain and the micro strain. Macro strain is the one, a sample can be either the tension or it can be under the compression. Okay. Tension compression, like d-spacing is going to increase in the tension case, d-spacing is going to decrease. In that case, we know that the n lambda equal to 2d sine theta. So similarly, theta will decrease. Here the theta will increase. Okay. We are just seeing the effect. So if you are seeing if you are seeing all of your peak in the XRD pattern, initially let's say for the ideal crystal, the peak was like this. Now, now you did something, you strained it in certain way. The strain can be in any way. You can even use the EQ cohesive channel again, where you can create the deformation in the sample. In this case, what we are seeing that the entire all the peaks, the 2 theta is decreasing. What does it mean? That you have created the tension in the specimen. Your entire the specimen is under the tension. This is the thing. Now the micro strain, it is the local strain. Okay. In this case, what can happen that, so here we can say that either the theta will increase or theta will decrease. Okay. So peak position, it will affect the peak position, we can say. Now in the case of micro strain, it can be within a grain. Now a grain or a particular region, it can be under the tension, and it can be under the compression. Now here, see, tension, it means that it is, let's say ideal is D naught. So in the case of tension, it will be more than D naught. Compression will be less than D naught. So in between them, a region will come where it will be the D naught itself. Okay. Now, what does it mean that our D spacing is continuously keep on changing here on this side, on this side. Okay. So we have created the defects in that. Okay. Now this strain is going to affect our broadening. Let's say we have the crystal which is neither in the tension nor in the compression, like at particular local region we are talking about. In that case, our broadening will be like this. While in this was the case 1. While in the case 2, where the tension and compressions are there, now the broadening will be something like this. Okay, this was the case 1, this is case 2. So the micro strain is going to affect the peak broadening. Okay, so this was the thing. So we need to remember this two part. If your entire specimen is under the, see, on an average, tension and compression, they are going to cancel out with each other. It might be possible that there is no shift in your specimen. There is no shift in the peak position. And you will think that there is no strain, but if there is a broadening is there, then the strain is there. The tensile and the compression, they are elongated. Okay, here it will be, the atomic spacing will be more, here it will be less. Okay, so the broadening the peak broadening will also tell the information of the microstrain, and the peak position shift, if all the peaks are shifted towards a particular side, either the left or the right, they are contributing toward the macrostrain. Okay, so based on this thing only, I have designed the question over here. How does the presence of microstrain in a material primary effect in the XRD pattern? Microstrain we are talking about. Can anyone answer like A, B, C, and D? It's very easy. We just now discussed. Everyone can answer this question easily. It causes a uniform shift of all the peak to the lower 2 theta. It causes uniform shift all the peak to the higher 2 theta. It creates new sharp peak that were not present before. Option D, none of the above. What do you think? Little tricky, right? What is the right answer over here? The options are designed quite nicely. Like we are expecting something like it cannot be the answer, then actually that is the answer. The answer is none of the above. The real what will be the right answer? The microstrain is going to affect the peak broadening. So question was easy. It's only due to the answer, the way the answer, the things I design. It's like this. Okay, little complicated, but if you know what macro is going to do, it is going to change the peak position. What micro is going to do, it is going to affect the peak broadening. If you know this part, you can able to answer it. Okay. Okay. Very good. Any doubt in the question number 9, guys? Okay. Since there is no, let's move to the next part. Question number 10. What is the effect of a uniform macroscopic tensile stress on the XRD peak? Okay. So it is specified here that it is a macroscopic tensile test, tensile stress. Very good. The Gitu has wrote the answer. The option B is the right answer. So in the tension, we know that when we are when the specimen is in the tensile test, tensile stress, it means that the D spacing is more, and so which is going to reflect that theta will be the less. Okay, that the peak will shift to the lower theta, lower angle side, right? Very good. Let's move to the last part. This part. Important effects on matter, the absorption and the temperature factor. Okay, so this part has been covered in the class. That the absorption, we know that. Again, we are talking from the cylindrical specimen perspective, let us say. So we know that let's talk about how the intensity is going to affect. At certain high temperature, let's say we are also incorporating the temperature effect. So what was the temperature effect? E to the power of minus of 2m. On the axis, we have 2 theta. It can be like, we can see that the intensity will go something like this.